Hello everyone. So today's topic is torque acting on a current carrying loop placed in a uniform magnetic field. This is the topic for today's class. We will find out the expression of this. So this is the topic torque on a current carrying loop placed in a uniform magnetic field. So for this, first we will consider a current carrying loop of shape of rectangular shape. Yes. So let's say we have a loop, a rectangular loop like this, which is placed in a uniform magnetic field. Sorry, uniform magnetic field, which is represented by the equidistant parallel lines like this, and let the name of the loop be PQRS, and a current I is flowing in the clockwise direction through this loop, and let the magnetic field be B. The magnetic field in which it is placed, let it be B. Now we need to find out the torque. Now to find out the torque, first we need to find out the forces acting on each side of the loop. So as you can see from here, if we actually want to find out the force on PQ, that is this top side, and RS, as you can see the direction of the current are opposite, and it will always make direction of the currents are opposite, and it will always actually have the same amount of current flowing through it. So their magnitude, the force acting on them, which is given by, we know that force, so if we write FPQ, it will be given by what? The amount of current multiplied by its length. So let the length of this side PQ be B, and this length be A, that is the PR. So I B multiplied by IL cross B, so IL cross B. Similarly, if RS, that is the force acting on RS, will be I B cross B. Now these two eyes are in opposite directions. So they will have the same magnitude, but they will act in the opposite direction. And as is the configuration of this loop here, you can see these two forces will also have the same line of action. IA cross B means IB cross B means these two forces must be always perpendicular to B as well as, I mean, the small b length as well as the magnetic field B. So that this direction is fixed. Similarly for RS it is fixed and they will always act like this. So you can see from here they must act in this line. So if I write, they both must be perpendicular to small b as well as capital B. So this should be the direction of FPQ and this should be the direction of FRS. They both must be equal and opposite and they also must have the same line of action. As you can see, they are acting along the same line. So they will not produce any torque. So due to the same line of action, no torque will be produced. This will happen for these two forces, as you can see. Whatever may be, they are perpendicular to the plane consisting of the magnetic field B and the side B. So if we actually consider a plane like this, they will always be perpendicular to that plane. This is the plane of the page which is containing B. So this B and this B, if we consider a plane like that, they will always be perpendicular to this plane, these two forces, and opposite. So they will not produce and their line of action will be same, as you can see from here, always. Whether the loop is rotating or not, the line of action will remain same. It will not change. They are equal and opposite and their line of action is also same. Now what about the forces FPR and FQS? So let's say I am taking this diagram here. So here you can see that now if we want to find out FPR, it will also be equal and opposite to FQS because the direction of the current is opposite in QS. This will also be same and its magnitude should be what? Now it should be I. What is the length of here? A cross B. This should be the magnitude. So now you can see here these I and B will be always perpendicular to each other, always. Whatever be the orientation or the position of the loop, these two I and B are always perpendicular like this. Whatever, if it is rotating also, I is always upward like this, B is always like this. Whatever may be the direction or the orientation or the position of the loop. You can see from this diagram. Whatever. It is always perpendicular. So the angle between them will always be 90 degrees. So the magnitude will always be only this. IAB. This should be the magnitude. Now, though the magnitude is same and they are acting opposite to each other, their line of action will actually vary with the rotation of the loop. But as you can see, if we actually consider the loop to be like this, let's say the loop is like this. So that its normal to the loop is actually perpendicular to the magnetic field, like this. In that case, the normal distance between the line of action of the two forces, it will be only this, because in this case FPR and FQS will act outward and inward. Sorry. You can see this is the case where the current and the magnetic field are perpendicular to each other. So according to left hand rule, Fleming's left hand rule, we will have F peer having a direction normally outwards from the plane, F peer, and FQS will have a direction normally inward to the plane. And now the distance between the lines of action, as you can see, will only be the width B of the loop. This is the maximum. But if we consider the loop to be like this, when actually the perpendicular to the surface of the loop is parallel to the magnetic field, so loop will look like a straight line like this. The previous case, like this. This one. In that case, you can see now the line of action of FPR and QS will be same, so they will not produce any torque. So depending upon the orientation of the loop, the line of action will actually vary. That is, the distance between the line of action of these two forces will vary. And let at any random orientation, the normal to the loop, this one, is making an angle theta with the magnetic field. This is the direction of the normal to the loop N, and it is making an angle theta with the magnetic field B. Now in this case, what should be the torque produced by these two forces? So to find out that, we have already found out what is the magnitude of the force. Torque is, we know, torque tau is F multiplied by normal distance between the lines of action. Normal distance between the lines of action. Now in this random orientation, what is this distance between these two forces? That we need to find out. So to find out that, we need to draw another diagram which is actually the view of the loop from the top. So let's say we are taking another diagram. Here, this is a view from the top, and this is one side A, that is the top side. This is actually the direction of the force F. PS. You can see this one was, sorry, PR, and another one was QS. So this is FPR, and here FQR is acting opposite to FPS. Like this, and the currents are actually from the top at this point, that is the one end of the loop having this length as B, this whole length as B. The current here, which is actually clockwise, it will be actually outward from the top. It will look upward because the current is going upwards. I'm writing here, this is top view. From the top, if we actually draw a diagram, and here the current is going downwards. So the current will be downwards, and we represent downward current as a cross downwards. This will be the diagram. And what about the angle theta here? The angle theta is the angle between this. So if we actually, this is the line of action. So if we actually want to find out the normal distance between the line of action, this should be this one. That is this is the line of action of FPR. This is the line of action of FQR. This distance will give us the line of action. This one. This is, let that be X. This distance. So what is theta here? Theta is angle between the normal to the plane and the magnetic field. So magnetic field will also be in this direction from the top. So if we actually draw the normal, this is actually the direction of the normal to the loop, and it is making an angle theta with this, because this direction is representing the direction of the magnetic field from the top. You will see magnetic field is always there, and it is in this direction, like this. So the direction of the magnetic field is this. So what is this X in terms of theta and B from this diagram? X, you can see if this angle is theta, this angle must be 90 degree. This angle, that is the angle made by the normal with the surface. So this angle is theta, this is 90 minus theta, this is 90, means this angle must be theta. Then only in this triangle we will have the sum of the angles as 180 degree. So this angle is actually theta, this one. I am removing this. So it will be better to understand. This angle is actually theta. So if this angle is theta, from this triangle you can see X by B will actually give us X is the normal for this triangle and B is actually the hypotenuse. So X by B will be equal to sine theta. So X will be equal to B sine theta. Therefore, the torque tau is the force multiplied by X. The magnitude of the force is IAB, and X we have found out is B sine theta, where B is the width of the loop. So it will be IAB capital B sine theta. Now what is actually IAB? AB is the area of the loop, and IAB we can write it like this: I A cross B, because theta is the angle between the area vector and the magnetic field. So actually this will give us the torque acting on it, and this term IA is actually called the magnetic moment of the loop, because dot cross product we have sine theta. So IAB capital B sine theta is actually IA cross B, where IA is the vector representing the direction of the normal to the area vector A, and B is the direction of the magnetic field. So this is actually the torque acting on a current carrying loop. It is bit difficult to actually conceptualize, or it is a bit difficult to actually imagine the diagram, because it is actually a 3D diagram and we are doing it in the 2D page. That is why there are some difficulties to actually comprehend this thing. First of all, you have to remember, if we go to the first page, yes, these two forces are FPQ and FRS. These two forces will be equal and opposite, and they will always have the same line of action. Always, whatever may be the orientation of the loop. So they will not produce any moment. Okay, whatever may be, they will always act like this, upwards, downwards, in the same line. Whatever may be the orientation. But for the sides PR and QS, they will actually produce the torque, because though the force on them will act opposite to each other and they will have the same magnitude, but their line of the distance between their lines of action will vary as the loop will rotate. Because actually you can see these two forces, if you go to the next page, this FPR and FQS, these two forces, it will actually try to rotate this loop clockwise always, because it is acting in this direction. You can see actually, if I draw here, FPR will be what? FPR will actually have a direction like this, and FQR will have a direction like this. Sorry, FQS. So they will actually try to rotate the loop clockwise, and when actually the surface of the loop will become parallel to the magnetic field, in that case there will be no torque acting. Sorry, not the surface, the normal. That is when the surface will become perpendicular to the magnetic field. In that case, no torque will act. So, what will be the magnitude of the force of FPR and FQS? You can see the magnitude will be IAB. This one. Again, it will be IA cross B, and here these two forces, whatever may be the orientation of the loop, these two forces will always have a perpendicular direction with the magnetic field. So the angle between them will always be 90 degrees. So the magnitude of the force will be this. Now this will be the magnitude of the force, and as the loop will rotate, the distance between the lines of action will actually vary. As you can see here, when the loop is like this, that is the plane of the loop is parallel to the magnetic field, the distance between the line of action of the forces FPR is like this, inwards, and FQS is outward. So, sorry, FPR is outward, yes. Now FPR will be inwards. This should be crossed. Yes. If we consider the current is flowing like this should be crossed, this should be drawn. So then in that case the normal distance between these two will be maximum. But if we consider here like this, when the plane is actually perpendicular to the normal, in that case both the lines of action will be same, and there will be no torque acting. So then what we are doing, we are actually considering any random orientation where the loop is making an angle theta. That is, the normal to the loop is making an angle theta with the direction of the magnetic field. In that case, what will be the torque? The torque, to find out the torque, we must actually multiply the force with the distance between the lines of action. So if we actually draw a diagram which is representing the top view of the loop, we will see FPR is acting like this, FQR like this. This is B, that is the width of the loop, and the angle between the normal to the loop and the magnetic field, which is also the direction of the normal distance between the two forces. We will find out that the normal distance is at x is actually b sine theta. So what will be the torque? Force multiplied by x, that is IAB b sine theta. AB will give the area of the loop. So vectorially it can be written tau as vector tau, that is the torque, is IA cross B. Okay, where A represents the area of the loop, B is the magnetic field, and this term IA is actually called the magnetic moment of the loop. I hope you have understood. Thank you.